Dear learners, welcome to this session of marketing research. In the previous session, we discussed simple regression analysis in which one independent variable, say x, was used to predict the dependent variable y. The main objective of regression analysis is to explain the variation in one variable called the dependent variable based on the variation in one or more other variables called the independent variables. The number of independent variables in a regression analysis could be one or more. Even in case of more than one independent variable, a best fit model can be developed using regression analysis. So, regression analysis with two or more independent variables or at least one nonlinear predictor is referred to as multiple regression analysis. In this session, we will discuss multiple regression analysis where several independent or explanatory variables can be used to predict one dependent variable. Learning outcome of this session are explain the nature and methods of multivariate regression analysis, discuss concept of coefficient of multiple determination, adjusted coefficient of multiple determination and coefficient of regression. Describe the statistical significance test for the regression model, discuss the assumptions and key considerations for multivariate regression analysis. Let us recall from our earlier session that regression analysis is probably the most widely applied technique among the analytical models of association used in marketing research. Regression analysis finds out the degree or relationship between a dependent variable and a set of independent variable by fitting a statistical equation through the methods of least square. Whenever we are interested in the combined influence of several independent variables upon a dependent variable, our study is that of multiple regression. For example, demand may be influenced not only by price but also by growth in industrial production, the extent of import prices of other goods, consumers' income, taste and preferences and so on. Marketing researchers could use regression for explaining percent variation in dependent variables caused by a number of independent variables and also problems involving prediction or forecasting. For example, in demand analysis, demand is inversely related to the price of normal commodities and we may write as D is equal to A minus BP, where D is the demand which is the dependent variable and P is the unit price of the commodity, an independent variable. This is an example of simple linear regression equation. The multiple linear regression model is the prototype of the single criterion and multiple predictor association models, where we would like to study the combined influence of several independent variables upon one dependent variable. If P is the consumer price index and Q is the industrial production index in the percentage, so in the preceding example, we may be able to study a demand as a function of two independent variables P and Q and we can write the equation as D is equal to A minus BP plus CQ as a multiple regression model. The objectives of marketing researchers in using regression analysis are to study a general underlying pattern connecting the dependent variable and independent variable by establishing a functional relationship between the two. In this equation, the degree of relationship is derived, which is a matter of interest to the researcher in his study. The other objectives can be to use the well-established regression equation for problem involving prediction and forecasting. One more objective can be to study how much of the variation in the dependent variable is explained by the set of independent variables. This would enable to remove certain unwanted variables from the system. For example, if 95% of the variation in demand in a study could be explained by price and consumer rating index, the researcher may drop other factors like industrial production, the extent of imports, substitution effects, etc., which may contribute to only 5% of the variation in demand, provided all the causal variables are linearly independent. Now, let us take assumptions of linear regression. The simple linear regression model rests upon several assumptions to ensure the reliability and validity of its results. The first assumption can be normal distribution of errors. The error term representing the difference between observed and predicted values is assumed to be normally distributed. This implies that for any given value of the independent variable, say x, the corresponding value of the dependent variable, say y, are normally distributed around the regression line. Other assumptions can be zero mean error. The average value of the error term is expected to be 0. This condition indicates that the model's predictions are unbiased, centered correctly with no systematic overestimation or underestimation of the dependent variable. Then the constant error variance, this assumption is that the variance of the error term should remain constant across different values of the independent variable. This homogeneity of variance, also known as homoscedasticity, ensures that the model's predictive power is consistent throughout the data range. Then the next assumption is independent errors. The errors for different observations are assumed to be unrelated to each other. This means that the error associated with one observation does not influence the error of another, implying that the data points are not correlated. The next assumptions can be fixed independent variable. The value of the independent variable are predetermined and not random. This assumption is crucial as it allows for the estimation of the regression coefficients without considering the variability of independent variable. Now, let us see the computational aspects of multiple regression. As we have seen earlier, that the simple regression model with one independent variable is presented with respect to population parameter beta 0 and beta 1 as y is equal to beta 0 plus beta 1 x, where beta 0 is the population y intercept which represents the average value of the dependent variable when x is equal to 0, and beta 1 the slope of the regression line which indicates expected change in the value of dependent variable y for per unit change in the value of independent variable x. In the multiple regression model, there are at least two independent variables, and the general form of the multiple regression model can be expressed as y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta k xk plus the error term epsilon. To understand the concepts clearly, let us study a case of two independent variables. Estimated regression line based on sampling can be written as y is equal to b0 plus b1 x1 plus b2 x2 plus u. Here there are three parameters b0, b1 and b2 that are to be estimated. b0, b1 and b2 are estimates of beta 0, beta 1 and beta 2 obtained through the methods of least square by minimizing the error sum of squares, and we can use the formula for b1, estimated b1 is equal to summation of x1y multiplied by summation of x2 whole square minus summation of x2y multiplied by summation of x1 x2 divided by summation of x1 square multiplied summation of x2 square minus summation of x1 x2 whole square, and b2 can be estimated by using the formula as b2 is equal to summation of x2y multiplied by summation of x I square or x1 square minus summation of x1y multiplied by summation of x1 x2 divided by summation of x1 square multiplied by summation of x2 square minus summation of x1 x2 whole square. And once we get the value of b1 and b2, the b0 can be estimated as b0 is equal to y bar minus b1 x1 minus b2 x2, and this x1 is a deviation from the mean x1 bar. So, x1 is equal to x1 minus x1 bar, x2 is equal to capital X2 minus average of x2, and y is equal to capital Y minus y bar. So, after providing an overview of the regression model's underlying assumptions and the formula we can use for estimating B0, B1 and B2, let us take a numerical example to help make the concept clear. Suppose that a marketing researcher is interested in customers' preference dependent variable and it can be denoted as Y for a nutritious diet of ready to eat cereal based on the amount of protein, say x1 independent variable, and vitamin D, say x2 independent variable per standard serving. So, here there are two independent variables, one is protein x1 and others vitamin D x2. On a preference rating scale ranging from 1 dislike extremely to 9 like extremely well, the researcher collected the data from 10 ready to eat cereal customers. The data is presented in table 1. Here it is given in column 1 the respondents 1 to 10, in column 2 preference Y values are given, in column 3 protein intake is given, and in the last column the vitamin D intake is given. So, based on this data we can calculate the x1 bar as 43 divided by 10 is equal to 4.3, y bar is equal to 430 divided by 10 is equal to 4.3, and x2 bar is equal to 40 divided by 10 is equal to 4. Now, we can get the value of x1, x2. So, x1 is equal to x1 minus x bar. So, we get the value of x1. Similarly, we can get the values of x2 by subtracting x2 bar from the x2. After getting x1, x2, we can get the x1 square, x2 square, and multiplying x1, x2, we will get the values of x1, x2. We can calculate the y and the x1 y, x2 y. So, you can get all these calculations in table 2. After this, we can estimate by using the given formulas. So, B1 estimated B1 is equal to 62.1 multiplied by 66 minus 60 multiplied by 57 divided by 70.1 multiplied by 66 minus 57 into 57, that means square of 57. So, by putting this value we get the value of estimated B1 as 0.493. Similarly, by putting the values of x1, x2, we can estimate the B2 and we get the value as 0.484, and by putting this value of B1 and B2 we can get the estimated value B0 as 0.247, and by substitution the values B0, B1 and B2 in equations, we get the regression model as y cap is equal to 0.247 plus 0.493 x1 plus 0.484 x2. Here B1 and B2 are called partial regression coefficients. B1 value we have estimated as 0.493 and it denotes the change in y per unit change in x1 when x2 is held constant. Similarly, B2 is estimated as 0.484, denotes the change in y per unit change in x2 when x1 is held a constant. This estimated regression equation indicates that the protein intake is positively related with preference for ready to eat cereals, as is evident from the positive value of its coefficient as 0.49. Similarly, the vitamin D intake is positively related to the preference for ready to eat cereals, as the coefficient for the vitamin D variable is positive, as the estimated value is 0.48. The result indicates that if the protein intake goes up by 1 unit, the preference rating for ready to eat cereals will go up by 0.49 units while keeping the vitamin D intake constant. If the vitamin D intake goes up by 1 unit, preference rating for ready to eat cereals will go up by 0.48 units while keeping protein intake constants. Now let us discuss the significance of these calculated values. You may find here calculating these values tiresome and time consuming, but software packages such as Excel, SPSS, SAS or R can simplify the calculations by providing calculated tables as output. So the importance is on understanding the significance of these values for practical implications. So in table 3 is for the coefficients, and you can see from table 3 that the values of standardized beta coefficients are same as that we have manually calculated as B0 0.247, B1 0.493, B2 0.484. In the table 3, the values of standardized beta coefficients are also given for protein intake as 0.473 and for vitamin D intake 0.450. You would obtain the standardized coefficients beta if you standardize all of the variables in the regression, including the dependent and all of the independent variables, and ran the regression. By standardizing the variables before running the regression, you have put all of the variables on the same scale. And you can compare the magnitude of the coefficients to see which one has more of an effect. You will also notice that the larger betas are associated with the larger t values. For the validity of the regression equation, we look first at the coefficients of multiple determination R square and multiple correlation coefficient R. In the model summary given in table 4, for the given case R square is equal to 0.783 and R is equal to 0.885, which is a satisfactory one, indicating that the preference stating Y is linearly related to protein intake X1 and vitamin D intake X2. It tells that 78.3% of the variation in Y is explained jointly by the variations in protein and the vitamin D intake, that means X1 and X2. Let us discuss the significance of adjusted R square given in table 4. As predictors are added to the model, each predictor will explain some of the variance in the dependent variable, simply due to chance. One could continue to add predictors to the model, which would continue to improve the ability of the predictors to explain the dependent variable, although some of this increase in R square would be simply due to chance variation in that particular sample. The adjusted R square attempts to yield a more honest value to estimate the R square for the population. In table 4, you can see the value of R square is 0.783, while the value of adjusted R square is 0.721. When the number of observations is small and the number of predictors is large, there will be a much greater difference between R square and adjusted R square. By contrast, when the number of observations is very large compared to the number of predictors, the value of R square and adjusted R square will be much closer. Now see the hypothesis testing for linearity through the ANOVA. So as we know, the step 1 set null and alternative hypothesis. Here null hypothesis is there is no linear relationship between the preference and protein intake and vitamin D intake. That means H0 such that beta 1 and beta 2 is equal to 0. And alternative hypothesis H1 is there is linear relationship between the preference and protein intake and vitamin D intake, and it can be represented as H sub 1 such that beta 1 and beta 2 is not equal to 0. Step 2 is determine the appropriate statistical test. In this case, the test is ANOVA, that is means analysis of variance. Step 3 set the level of significance, and we know the level of significance is assumed as 0.05. Step 4 is define the critical region in terms of the test statistic. Now we have to define a critical value that separates the acceptance and rejection regions. If the computed value of the test statistics fall in the acceptance region, the null hypothesis is accepted, otherwise it is rejected. At the given level of significance, alpha is equal to 0.05 and the degree of freedom 2 and 7, 2 as for numerator and 7 for denominator. The tabular F value from table 5 is 4.74. It means if the computed test statistics F is less than or equal to 4.74, the decision is to accept the null hypothesis, and if the computed test statistic f is above 4.74, the decision is to reject the null hypothesis and accept the alternative hypothesis. Step 5 is collect the sample data. Collected sample data is already given in table 1. Step 6, analyze the data. The calculated ANOVA values are shown in table 6. You can see from the table that the calculated F value is 12.65. So, step 7, arrive at a statistical conclusion at the 5% level of significance and at the 2 and 7 degree of freedom of the numerator and denominator respectively. The tabular F value from table 5 is 4.74. The observed value of F is calculated as 12.65, which is higher than the tabulated value of 4.74 and falls in the rejection region. Hence, the statistical conclusion is to reject the null hypothesis and accept the alternative hypothesis. Now, the step 8 is discuss the statistical decision in terms of the marketing research problem. On the basis of hypothesis testing, it can be concluded that there is linear relationship between the preference and protein intake and vitamin D intake. So, the null hypothesis that is stated as there is no linear relationship between the preference and protein intake and vitamin D intake is rejected, as there was strong evidence to support a change and an alternative hypothesis was accepted. You can also observe from the ANOVA table 6 that the significant value or the p value associated with the f value is small, that it is 0.005 in comparison to the alpha level 0.05. So, it can be concluded that the independent variables reliably predict the dependent variable. Now, key considerations for multiple regression analysis. When conducting a multiple regression analysis, carefully consider the following. The first is assumptions. Ensure your data meets the underlying assumptions of linear regression, including linearity, homoscedasticity, normality of residuals, and absence of multicollinearity. Violation of these assumptions can significantly distort the model's output and lead to erroneous conclusions. Second, model evaluation and fit. The regression equation should be validated statistically. A well-fitted model accurately represents the relationship between variables. Metrics like R squared, adjusted R square, and mean squared error provides insight into model fit. However, it is crucial to balance model complexity with interpretability. Overfitting can lead the models that perform poorly or new data. Then variable selection and multicollinearity. The choice of independent variable is crucial. Including irrelevant variables can reduce model efficiency, while omitting important ones can bias results. Moreover, high correlations between independent variables, that means multicollinearity, can inflate standard errors, making it difficult to assess the individual impact of each predictor. And for forecasting the dependent variable, the independent variable should be forecast first. For example, if demand is a function of the price index and production index established by a multiple regression model, then to forecast demand for the next period, it is imperative first to forecast the price index and production index and then substitute them in the model to get the forecast for demand. This is one of the limitations of regression forecasting. Then the next key consideration can be interpretation and causality. Regression coefficients quantify the relationship between each independent variable and the dependent variable, holding other variable constant. However, correlation does not imply causation. Careful interpretation is necessary to avoid overstating the causal impact of predictors. So, with this we can conclude the session. In this session, we have explained the nature and methods of multivariate regression analysis. We discussed concept of coefficients of multiple determination, adjusted coefficients of multiple determination and coefficients of regression, described the statistical significance test for the regression model and discussed the assumptions and key considerations for multivariate regression analysis. Now, you can check your progress by attempting these problems. The question 1 is, regression analysis helps to determine option A, the cause and effect relationship between variables, B, the degree of relationship between a dependent variable and the set of independent variable. Option C, the correlation between two variables. D, the classification of data into groups. Question 2, the method used to fit a statistical equation in regression analysis is option A, least square method, B, maximum likelihood method, C, average deviation method, D, standard deviation method. Question 3, the coefficient of determination, that means R square, in multiple regression represents option A, the proportion of variance in the dependent variable explained by the independent variables, B, the correlation between the dependent and independent variables, C, the error terms in the regression equation, D, the slope of the regression line. Question 4, multicollinearity occurs when option A, there is a perfect linear relationship between two or more independent variables, B, the dependent variable is highly correlated with the error term, C, the regression model is not linear, D, the sample size is too small. Question 5th is, the adjusted R square is used to option A, penalize the addition of unnecessary independent variables, B, increase the value of R square, C, measure the correlation between variables, and D, none of the above. So, with this we end the session here. Thank you. Happy learning.